Okay. Good morning, students. Today, in conjunction with the last lecture, I am going to explain the next concept, that is concept of frequency reuse channels. Okay. Actually, by the name, we came to know that in which frequency is to be reused. Same frequency is to be reused. That's why the concept name is your frequency reuse channel. Actually, we know that in a radio channel, we use a pair of frequencies. One for the each direction, that is one for the transmission, and other is for the receiving operation. So let us suppose we have a radio channel that is operated at the frequency f1, and this covers the area that is C1, and the cover and the this frequency channel radio channel covers the area that is C1. So coverage radius and cover the area by using the cell C1, and the coverage radius is denoted by capital R. So these same F1, C1, and R can be used in the another coverage radius, another in the another area with the distance d. Now this can be explained with the help of our diagram. Yeah, now you can see C1 is the cell and the frequency used by is F1. Let us suppose C1 is your cell and the frequency used is 100 megahertz. Let us suppose. So this is the cell which is at Amritsar, and now you can Amritsar at the Jandiala side. And now in the second cell, let us suppose I am using this cell again C1, and with the same frequency at the G and U side. So that's why same frequency can be used in the two different areas. So frequency is reused, and the C by I is your carrier to interference ratio, and this is equivalent to your gamma. And the radius of this cell is capital R, and the power related to that cell is P naught. Okay, and this is the d distance between these two cells. So the distance between the two cells, that is your capital D. So Q is equal to D by R. This is the D by R ratio, where D is the distance between the two same cells having the same F1 frequency using the same frequency band, and the R is the radius of that particular cell. So this diagram shows the frequency reuse at d distance away, and the ratio. This diagram shows the ratio of d by r. Okay, next, coming to the next slide. So frequency reuse ratio, that is noted by small q, and it is given by q is equal to d by r. And the frequency reuse ratio actually is referred to as your co-channel reuse ratio. Actually, co-channel means the same channel which is used. So co-channel means the same channel is to be used. That is, co-channel means your channel is here in the same area actually, or in the same city. That's why this is known as co-channel reuse ratio. If I am using the two cells in different cities, let us suppose one in Amritsar and second is Jalandhar, that will be not the co-channel. Okay, so co-channel, this is also known as your Q is also known as your co-channel reuse ratio, or also known as your co-channel reuse factor, and this is also known as your co-channel interference reduction factor, because we know that in the third co-channel interference reduction factor, as you know that if I am using the two same frequencies at different in different area, but there is a possibility of some sort of interference in that. So that's why this factor also tells us how much distance d should be there between the two cells, so that our interference should not affect it too much. So that's why this factor is also decided the interference reduction factor also. So that's why this is also known as your co-channel interference reduction factor. Now come on to the next slide. Which are the various factors which influence your distance between the two cells? First is the number of co-channel cells in the vicinity of the center cell. Means how many co-channels are there? Co-channel cells are there in your area, means using the same frequency. Second is the how which is the type of the geographic area. It is the terrain contour or the your means geographic terrain contour is your flat or the hilly area or somewhat rural area. What type of the area? Third is antenna height, means how much antenna height is to be used, and this is also influence actually these factors. This also factor influence the distance. How much distance should be there between the two cells. And the last one is how the transmitted power, how much transmitted power at each cell site should be there, and this vector also influence the d, that is the distance between the two cells. So as long as our cell size is fixed, means the radius of the that cell size is fixed, so co-channel interference actually independent of the fourth parameter, that is your transmitted power. Means your interference, co-channel interference is not dependent upon the transmitted power which is used at each cell, that is p naught. So these were the some of the factors which influence our d. Now actually we know that reusing means we are using the identical frequency channel in different cells. Means we are using, if I am using the 100 megahertz in one cell, in second cell also I am using these 100 megahertz frequency. So reusing it is actually an identical frequency channel which is used in different cells. This is actually limited by the frequency reuse concept is actually limited by the co-channel interference between the cells, as I have already told with you. Because because there can be possibility of interference due to the use of same frequency in two different areas. So co-channel interference can become actually a major problem, and it is actually desirable. How always we require or desirable to find the minimum, what the minimum frequency reuse distance should be, that is d, in order to reduce our your co-channel interference. Means how much minimum frequency reuse distance should be there between the two co-channels, that is d, frequency reuse distance d between the two co-channels which are using the same frequency band, in order to reduce this your co-channel interference. Next is your, now you can see this is q is equal to d by r. Now you can see this is the these are the cells. Okay, 1 2 3 4 5 6 7, there are 7 cells in one geographic area, and again these 1 2 3 4 5 6 7, these same cells are used in another geographical area. So 7 and 7 will become as co-channel, 1 and 1 will become as co-channel, 2 and 2 becomes as co-channel, 3 3 4 4 5 5 6 6, these all are the co-channels in different areas. So actually, and the distance between these two channels is shown, and between the 6 also we can show the distance between the 5, and this distance should be how much this is we have to decide how much minimum this frequency reuse distance d in order to we have to find the actually minimum frequency reuse distance d, this d, in order to reduce our co-channel interference between the co-channel cells. So actually the real power, actually we know that the real power of the cellular concept is that interference is not, actually we know that interference is not related to absolute distance. Interference is not dependent upon the absolute distance between the cells, but actually it depends upon the ratio of your distance between the co-channel cells to the radius, that is d by r. D is the distance between the co-channel which are using the same frequency. 6 and 6, these all are individually working as cell. This is the cell number 6, this is the cell number 1, this is the cell number 2, this is the cell number 3, this is the cell number 4, this is the cell number 5, and this is the cell number 7. And one number cell, the frequency used by one number cell will be same as the frequency reused by the this one number cell in the another area. So that's why 1 1 2 2 3 3 4 4 5 5 6 6 7 7 and different geographical area will be worked as your co-channel. And the actually your interference is not dependent on only the absolute distance. This depends upon the d, that is the distance between the co-channels divided by radius of that particular cell. So that's why this is the q is equal to d by r. Now come on to the next diagram. As you can see different colors, these all are the same color cell will be your co-channel cells. You can see here marked as this color same. So these will be your co-channel cells, and this color is same. So that's why entire the whole geographical area is divided into the number of cells, and we can use the frequency reuse concept in that cells, and the same color cells will be denoted as your co-channel cells, and means they are using the same frequency. Okay, so next is your co-channel and adjacent channel cells. What is the co-channel cells and the adjacent channel cells? As you can see in the diagram, I will explain you in easy way. These 6 and 6 will be treated as your co-channel cells, whereas this one, this 6 is surrounded by five number cell and one number cell. So 5 and 1 will be act as adjacent cells. Okay, 6 and 6 in this area and 6 in other area will be treated as co-channel cells, where and these co-channels uses the same frequency. Okay, and 6 is surrounded by two other cells, that is 6 is surrounded by three other cells, 1 7 5. So these are the adjacent cells for the 6, and they all are using the different frequencies. Means 6 is, if 6 is operated at 100 megahertz, 1 can be at your 200 megahertz, 5 can be at 300 megahertz, 7 can be at 500 megahertz. So these consecutive cells are known as your adjacent cell. So the concept of your co-channel and adjacent channel cells are the cells which uses the same set of frequencies. So that type of cells are known as your co-channel cells, and the co-channel cells are actually physically part, and the distance between that is given by capital D, so that it should not cause the co-channel interference. And the second is here the space between the adjacent co-channel cells is filled with other cells that is use different frequencies. I have already told you 157 uses the different frequencies to provide the actually the provide to providing the frequency isolation between the different cells. So next is your frequency reuse scheme. Next concept is your frequency reuse scheme. So as this frequency reuse concept can be implemented in our time domain and space domain also, and in the time domain actually in time domain we can use the same frequency with different time slots. Means we can use the same frequency band, single frequency, but time is divided into time slots. So that type of your multiplexing is known as your time division multiplexing. And the frequency reuse, this was the in the case of your time domain, we are using the using the different time slots. That's why this is your time domain time division multiplexing. And in the space, in the second one is your, it can be implemented in the space domain also. In the space domain, we can divide the frequency reuse concept into the two categories, which is shown in the next slide, in two categories. First one is we can use the same frequency. Same frequency can be assigned in two different geographic areas such as AM, FM. As you know that FM is operated as in any city. If you go to the Amritsar to Jalandhar, FM is operated as same frequency. Let us suppose FM radio is operated as same frequency, 104.8. 94.5. So it means that we are using the same frequency assigned in two different geographic areas, such as your amplitude modulation, frequency modulation, radio stations. These uses the your same frequency, but in different cities. Now, second one scheme is applied in the space division, as same frequency repeatedly we can use in same general area one in one system. And actually, this scheme is actually used in your cellular systems. And there are so many co-channel cells. We know that I have already discussed with you. If you are using the frequency reuse concept, then there will be co-channels. There are so many co-channels in that. So the total frequency spectrum, if we I can divide my total frequency spectrum which is allocated to me, to our system, that will be divided into k frequency reuse patterns. Means we can use the frequency reuse patterns in the k divided into k. K can be 4, k can be 7, k can be 12, or k can be 19. Now you can see, I will show this k is equal to 4, k is concept of k is equal to 7, 12, or 19, as in the next further slide. As you can see, 1, 2, 3, 4. Then again 1, 2, 3, 4. Then again 1, 2, 3, 4. Means only 4 cells in whole geographical area is divided into your 4 cells, and these 4 cells be repeated in different areas. Okay, let us suppose at the Jandiala site I have divided my whole geographic area under the Jandiala site is into the 4 cells, and these again 4 cells on the GND site, or on the Veta site. We can also use these 4 only cells, 4 cells, repeating these 4 cells again and again in any geographical area in a same city. Now k is equal to 7. So 1, 2, 3, 4, 5, 6, 7. Okay, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. So this is the k is equal to 7. Means whole geographical area in any side will be divided into 7 cells. So in this 4, in this 7. So this is dark. This is these 7 cells is drawn as dark solid line. So this is another, this is another, this is another, this is another, this is another 7 cell pattern, and the one in this, one in this, one in this, one in this, one in this. These all are the co-channel, whereas 2, 3, 4 will be as your adjacent channels. Okay, adjacent channels. Now, in the similar with the similar concept, 12 means whole geographical area in any site is into the divided into 12 cells, and these 12 cells be repeated in any side of the area. Okay, similarly in that last, in that this is where k is equal to here 19. So 19 cells will be there in any area, and this group of 7, group of 4, group of your 12, group of 19, this is known as your cluster. A group of cells is known as your cluster. So this is the one cluster, second cluster, third cluster. This is the one cluster, second, third, fourth, fifth, sixth, seven. And similarly with this, we can also have the group of 12. That is, group of 12 cells is known as your cluster. So here group of 19 cells is known to be as your cluster. So cluster actually word which is used for the grouping of the cells. Next is here, now this was the concept of that. Now I will explain cluster in detail in the next slide. So it is a group of cells that makes use of all the available radio spectrum. Means whole area is divided into number of cells. It can be 4 cells, it can be of your 7 cells, and that uses the all available radio spectrum. And second is cluster has n cells with unique and disjoint channel. Means unique cells are there and unique cells are there. Since adjacent can't be used the same frequency, you know that adjacent cells having the different frequency. So the total frequency is allocated, which is allocated, that is divided into the one cluster over the cluster, and that frequency allocation is always repeated for the other clusters in the system. And the number of cells in a cluster is known as the cluster size, Means if a cluster contains the 7 cells, so the cluster size will be your seven. If it is using four, then the cluster size will be your four. So, or you can say also cluster size or the frequency reuse factor, that is 1 by n. That is 1 by capital N. And capital N can be 4, capital N can be 7, capital N can be your 12, capital N can be your 19. Okay, so this was the concept of your cluster. So further I will show you the clusters. You can see A, B, C. If I am designated the cells are in the alphabet form, A, B, C, D, E, F, G. This is the cluster number 2. This is the cluster number 1. Again using these A, B, C, D, E, F, G. Same A, B, C, D, E, F, G. This is the cluster 3. So group of cells is known as your cluster. Okay, and next is next slide. You can see how frequency reuse pattern is depends on the two variables, that is I j or j I. If I am taking the 1 comma 1 combination, means I is 1, j is 1, then cluster size will be given by this formula, I square plus j square plus I into j. If I am putting this 1 square, I am putting I as 1, 1 square will be 1, then j square, that is 1 square, that is 1, then I into j, 1 into 1 is 1. So 1 plus 1 is here 3. Similarly, for other pattern frequency, we use 2 comma 0. For other values of ij, 2 comma 0, 2 comma 1, 3 comma 0, 2 comma 2, we can calculate the cluster size. So cluster size here can be your 3, 4, 7, 9, 12, 13, 16, 19, 21, 25, 27, 28. So means maximum we can also use it up to, we can go up to the 28. Means we can use whole we can divide our whole geographical area into the 28 cells also. So and this is the cluster size of frequency reuse. Frequency reuse here, frequency reuse factor. So whole, and this is if I am taking the one example, I am putting this 4 comma 0 in this. 4 square is where 16 plus j is where 0, 0 square is 0 plus I into j, that is 4 into 0 is 0. So this will be your 16. Similarly, if I am calculating for 2 comma 1, 2 square is 4 plus 1 square is 1. 4 plus 1 is 5 plus 5 plus I into j, that is 2 into 1 is your 2. So 5 plus 2 is your 7. So this will give you, this ij value will give you your 7. 7 size, the size of the cluster is 7. Normally we can use it in the next slide. We can use the, you can see 1 2 3 4 in different. So this is the cluster size is 4, 5 different. So another cluster 1 2 3 4, then again another cluster 1 2 3 4. And if reuse vector is here 7, so 1 2 3 4 5 6 7, then again 1 2 3 4 5 another cluster. Cluster number 2 is in the blue. For cluster number 1, if I am taking the cluster number 1 as a yellow color, so 1 2 3 4 5 6 7, then in blue also 1 2 3 4 5 6 7, and in without color, in the white color 1 2 3 4 5 6 7. So here we are using the reuse factor as your 7. We can also use the reuse factor as k is equal to 12. So you can see this is the cluster number 1, this is the cluster number 2, this is the cluster number 3, and this is cluster number 4. Okay, so in each cluster we have maximum number of cells are 12. This is 12, this is 12, this is 12, and this is 12. And these 12, 12 in this, 12 in this, 12 in this, and 12 in this are your core channel, whereas others are in 4, 3, 11. These all are the adjacent cells for the 12. So this was the your concept of cellular structure for k is equal to 11. Sorry, k is equal to 12. Now further I will discuss with you what type of cells can be there. Okay, different type of cells can be there. There can be your femto cells, pico cells, and what are the operational environment means, where operating environment means where it can be used. In the next slide we are going. So this is the cellular system actually based upon your cellular size. If your cell type is your femtocells, means the cell diameter in that case will be your less than 10 meters, and this will be actually used in your PAN, that is personal area network. Then the next type of cell type is your picocells, and it covers the area less than 100 meter, and this is used for the indoor environment. Actually, all of the cell type uses the different radio link propagation and different technical cell design concept. Means different design concept is also used for the different type of cells. Now, third is your microcell. Microcell covers the diameter from 100 to 1000 meters, and it is basically applied for the outdoor to indoor and the pedestrian environment. Now the macro cells, which covers the area your greater than 1000 meters to few kilometers, and this is used in your vehicular and your high antenna environment. And the last one is your mega cells, which is mega means which is used for the your global coverage, and this is also again used for the vehicular and your high antenna environment. So these were the your different type of your cellular hierarchy based on the different size of the cell size, and how it can be what will be the updating environment for that type of particular cells. Now in the next slide I will discuss with you what is the frequency reuse distance. Okay, as I have already told you that frequency reuse distance is the distance between the two co-channels cells in different area, that is denoted by capital D, and the capital D is equal to under root, the formula for that is capital D is equal to under root of 3 kr, and where k is the frequency reuse pattern. As you know, I have already discussed with you, k can be your 4, k can be your 7, k can be your 19, k can be your 12. So k is the frequency reuse. So actually minimum distance which can be used for the which allows the actually same frequency to be used in different area. So this also depends on the your type of the geographical terrain, also the antenna height, and also the transmitted power on each cell site. So this is given by the formula D is equal to under root 3 kr, where r is the radius of that particular cell. Okay, next is here, as you can see, for k is equal to 4, the distance is your 3.46 r, and for k is equal to 7 it is 4.6 r, and k is equal to 12 it will be 6 r, and for k is equal to 19 it will be your 7.55 r. So these were the actually we know that if all the cell sites actually transmit the same r, then k, naturally k will be increased. Naturally, if all the sites transmitted the same power, that means k will be increased. If k will be increased, then definitely distance will increase, because because you know that d is directly proportional during this, d is directly proportional to the k. Okay, so if d is D should be increased if all the your cell site transmits the same power, and if D is increased, this reduces the distance between the two core channel. If it is increased, then naturally the core channel interference effect is less, or we can say that we can reduce the chance of core channel interference factor by increasing the value of D. So this is the frequency reuse distance. Actually we know that a large value of k is actually in practically we can say that we should have a large value of k is desired, large value of k is desired. But we know that total number of allocated channels are fixed, which are allotted to us. So if your k is too large, the number of channels assigned to each case cells naturally becomes small. So it is always true that if the total number of the channels in the k cells actually we if I am dividing the total number of channels in k cells is divided, as k increases, naturally the trunking inefficiency will be result. So if I will apply this same principle, then spectrum inefficiency is also there. If the total number of channels are divided into two network systems, serving in the same area. So spectrum inefficiency also increases. So we should not have the k too much large, or k should not be too much small. So obtaining the smallest number k involves the estimated co-channel interference. Naturally, if smallest number of k is used, then co-channel interference the estimated, and the minimum frequency reuse distance d due to d is to be used to reduce the co-channel interference. The smallest value of k can be your k is equal to 3 by obtaining the I and j is equal to 1. As you have seen in this table, I've already discussed with you, the smallest value for the k is your is 3 by setting your value I is equal to j is equal to 1. So the minimum value for the k is equal to 3, and for that we have to set the I is equal to 1 and j is, for getting the k is equal to 3, I have to set the value of I is equal to 1 and j is equal to 1. So in this table. Okay, now come on to the how this distance is to be calculated. 3.46 r. If I am putting the k value here 4, so under root of 3 into 4, that is 12. That is under root of square root of your 12. Yeah, if I will take that, then this will give you 3.46 and multiplied by the r. Similarly, if I am taking the let us suppose 12, so 3 into 12 is 36, or the square root of the 36 is here 6. So that's why this is the 6r. How we can calculate this value? I have already tell you. We are getting with this formula. We can get this value by using this formula under root of 3kr. Now so this now further this table shows the frequency reuse ratio and the cluster size. K is equal to q is equal to under root of 3k. Naturally, if k is 3, if I am putting this 3 into 3 is 9, and the square root of the 9 is here 3. So this is the cluster size, and this is the frequency reuse ratio. So if I am using k is equal to 3, then this will give you 3. Then if I am using 4, then 3.46, then 7, 4.58, then 9, 5.20, 12 is given by 6, and so on. So up to the 28, we can putting this value of k and calculating the value of q, corresponding value of q after taking the square root of that value. Okay, now compiling this concept. So last in the last we can say that actually the concept of frequency reuse channel, if all the cell sites actually transmits your same power, I've already discussed with you. So the value of k is not to be too much large or too much you're low. If k is large, then trunking efficiency result. If k is too much low, value is small, then there will be your spectrum inefficiency result. So we have to actually decide that the what value of k frequency reuse factor should be there, so that we can get the optimum output, optimum your performance. So in that case, I will discuss with you in further concepts that k is equal to 7 is k is equal to 7 frequency reuse factor will give you the optimum performance in the mobile communication. Now the next is your number of customers. Actually frequency reuse affects also affected by the number of your customers in the system. So actually if we are designing our mobile system, so how many customers are there in that area, and how during the busy hour will be considered, and also the we have to see actually both the size of the different cells which are used in that particular area, and the number of channels allocated in that area is to be discussed. So maximum number of calls actually per hour per cell actually is given by the traffic conditions, that is the number of customers at each particular cell. And after the maximum number of actually and frequency channels per cell has been actually implemented in each cell, we know that. And if now we are taking the maximum number of calls per hour per cell as a QI, small capital Q and subscript is I, QI, then we can assume that 60% of the year calls, that is 60% calls will be handled during the busy hours. So the efficiency nita c will be your zero point 0.6. So this will be given by the total loud subscriber traffic will be given by mt, and this concept can be explained by a numerical. Now I will do this numerical on the blackboard. I will share my screen with the blackboard now. Okay, based upon the number of customers in the system, I will discuss numerical based upon that. Actually, the numerical is during a busy hour, the number of calls per hour is given by QI, and for each of the 10 cells, means number of cells are here 10. 10. So number of cells are here 10. So during a busy hour, we are using the number of calls per hour, that is noted by QI, and for each of the 10 cells, means we are using the 10 cells, and number of calls on 10 cells are 2000, 1500, 3000, 500, 1000, 1200, 1800, 2500, then 2800, and then 900. And if I am assuming that 60% of the your mobile phones or the car phones actually used during this period, so the efficiency for that will be 0.6. I have already discussed with you. Efficiency I am taking at 0.6, 60%. And that one call is made per hour, per car phone. So find the MT, that is total allowed subscriber traffic. Total allowed subscriber traffic, or the number of customers in the system, or the number of customers in the system. So solution for that is, firstly I have to find the QT, and the formula for that is QI, I is equal to 10, because there are total 10 cells, number of cells, so I is equal to 1 to 10, and I have to add these 10 number of calls. 2000 plus 1500 plus 3000 plus 500 plus 1000 plus 1200 plus 1800 plus 2500 plus 2800 plus 900. So after summing these, I will get 17,200 calls per hour, per hour. Okay, per hour on these 10 cells. Now if I have to find the number of customers in the system, that is noted by the MT, that is the formula for the MT is QT by NI, sorry, QT by NC, nita C, that is nita C. So QT by nita C is given by 17,200. I have calculated QT as this, and divided by Q nita C, that is given as 0.6. So after dividing these two, I will get the 28,667 number of customers in the system. So also this will affect your frequency reuse concept. So this on this we can get the how many number of customers can be handled during your busy hour. Okay, now I will discuss with you the co-channel interference reduction factor, that is the next concept. In this concept, actually we have to get the value of k, so that on which we can get the optimum performance, that is the co-channel interference factor is less. For that, a short derivation is there. Assume that actually we are assuming that the size of each cells which are co-channels, the size of each cells in co-channel or your adjacent channels are roughly the same in any area, and the cell size is actually, we can determine the cell size with the help of your coverage area and the signal strength of in each cell. And if I'm taking the cell size as fixed. So we know that co-channel interference is independent of your the transmitted power on each cell. So we have received the threshold level on our mobile unit that is adjusted to the size of the cell actually. As we know that we have Q is equal to D by R, where D is the function of, you can see on the screen, D is the function of your Ki and C by I, where C by I is the carrier to interference ratio. It is given by the formula C by I is equal to, sorry, K is equal to 1 to Ki Ik. That is the value of, you can see use vector K, 1 to Ki Ik. So the Q is the co-channel interference reduction factor, and if Q increases, naturally if your Q is increases, then your co-channel interference will be decreased, because you know that radius is your fixed. If Q increases, distance increases, and if distance increases between the two co-channel cells, then interference also decreases. And D, as you can see, D is the function of your Ki and C by I. Ki is the number of co-channel interfering cells in the first tier, and C by I in the is the received carrier to the interference ratio at the our mobile receiver. Okay. Ki is the number of co-channel interfering cells in the first tier, means I will show you the diagram. In the first tier, this is the one number, cell number 1 is surrounding that. This is the tier number 1, first tier. In the second tier, this is 1 1 1 1 1. In the third tier, it will again 1 1 1. So in the first tier, Ki shows the number of co-channel interfering cells in the first tier only. I am considering this situation only. Okay. So actually, in the fully equipped hexagonal shaped cells, we know that we are using the hexagonal shaped cells. We have only a 6 co-channel interfering cells. Okay, one is this, and 6 are the co-channel interfering cells. 1, 2, 3, counting wise. 1, 2, 3, 4, 5, 6. So always there will be always 6 channel interfering. So Ki is your 6. That is the co-channel interference that can be experienced on both our cell site also, and in our mobile units also. So in the second tier, if I am taking now the RC, second tier actually I am taking the negligible effect, because distance is too much apart from these co-channels. So if I am taking the co-channel interference from the second tier of interfering cells is negligible, I am considering only the first tier. So if one is there, the effect of interference on this, if one consider in this second tier, the effect of interference from this cells to this particular cell is almost negligible. So only we are considering these 6 cells, 6 co-channel interfering cells. And the formula for that is C by I is equal to K is equal to 1 to Ki dk by R. Okay, as you know that 1 by, this is given by C by I, so further formula C by I is given by your 1 by your K is equal to 1 Ki I, that is dk by dr, that is your Ik. Actually we know that your Q Qk is your dk by r. Naturally, Q is equal to d by r. So Qk will be equal to r is fixed, dk by r. So only d will be factored. Qk is equal to dk by r. So here I have this formula. So dk by r is written as Qk, and the power is your minus gamma, where Qk is the co-channel interference reduction factor with the kth, that is kth means 6 co-interfering your cells here. Kth is your number of co-channel interfering cells in the first time. So further we have 2 cases for that, for considering that first case is this and second is this. In the first case, the signal and co-channel interference received by the mobile unit and the signal and co-channel interference received by the cell side. This is the, now you can see, this is the arrow. These arrows are I1 dash is co-channel interference cells, I1 dash, I2 dash, I3 dash, I4 dash, I5 dash, I6 dash 6. These will affects the co-channel interference will be given to your given by the mobile unit to the cell side. And in the second case, all the interfering cells to the your interference received by the cell side, and signal in the signal second is here, first is by the mobile unit, interference received by the mobile unit, and second is interference and the signal. Along with the signal, we are getting the interference also. Second is interference received by the cell side. So both the cases are shown. In this, both the cases are shown. First one is here by the mobile unit. SM is written over there. Second one is here cell side. Okay. So NM, if I'm taking NM and NB, are the local noises that will be generated locally at our mobile units and the cell sites respectively. So NBM, that is mobile unit, local noise generated at the mobile unit, and NB is the local noise generated at the cell site. If I am taking as small as possible, and this can be neglected in comparison with the interference level. Okay, so next, in continuation for that, uh, we have to find the value of your k actually. So as long as we are getting the carrier to interference ratio in the mobile unit and at the cell site, if I am taking as the same in both cases, these both cases same, then this will be our balance system. And in balance system, we can choose either one of the case, even though we can choose this case, or even we can choose this case. So for the analyzing purpose. So if I am assuming that all the decay are same, all the decay are same, so dk will be same and q is equal to qk, then c by I is equal to r minus gamma divided by 6 d of minus gamma. And we know that d by r ratio is known as q. So if I am taking the power upward, then q gamma that will be divided by 6, or q gamma is equal to 6 by, if I am multiplying 6 here with this, so cross multiplying, so q gamma will be 6 c by I, and the q is equal to 6 by c by I. The power for that is here 1 by gamma. Now if we are I am taking the normal cellular practice, then c by I is here 18 dB in that case. How is it possible? 10 log, basically I'm specifying that 18 dB is possible. So actually this is measured by this 18 dB is measured by the acceptance of the voice quality which is taken or present on our cellular mobile phones. So if I am taking without this value, without the value of dB, so 10 log c by is equal to 18 dB. Then log is equal to c by is equal to 1/8, because 18 is divided by 10, that is 1.8. So if I am taking the anti-log on the both sides, I will get 63.1. So carrier to interference ratio is 63.1. Okay. Now Q, we know that Q is equal to D by R. So 6 into, because there was 6 co-channel interfering cells, so 6 into 63.1 raised to power 1 by 4. Gamma is here 4. So 1 by 4 is equal to gives you 4.41. And this value is given by the k is equal to 7. This value of q is given by your given by the k7. I will show this how. That's why we are designing the c by I for k is equal to 7. So q is actually we came to know that q is not actually the function of transmitted power. So So our Q factor Q is can be actually related to the final set of cells, which are K cells, which are in the hexagonal shape. Now 4.41, if Q is equal to 4.41, then particular K value for that will be shown in the discussed in the previous table. I will show you now. 4.41. As you can see, 4.41 q is approximately in this vector 4.41. That's why k is equal to 7. I am taking the k is equal to 7 for that. Okay, so here we have calculated the c by I for k is equal to 7 k's. Okay, now we know that q is equal to under root of 3k. Okay, and we are getting the k is equal to, and this indicates the several cell pattern, seven set reuse pattern that is needed for C by, if I want to get C by I is equal to 18 dB. This was the concept of desired C by I from a normal case in an omnidirectional. Omnidirectional means our antenna, my antenna transmits the signals in all the directions. So with this I have completed this topic, and in the next lecture we will do the concept of your handoff mechanism. Till then, take care, and I'm ending this lecture. We will meet in the next lecture. Thank you.